Physics. Chapter 1, we're just kind of learning some of the basics. So we're just learning how to describe motion, how to draw motion with diagrams. Maybe we'll learn a little bit about vectors and a lot about units and the things, the little nuances about how we write down the things that we're going to be computing and stuff like that. So right off the bat here, we're going to describe some motion. We have a series of images here as a skier went over a nice big jump. It's clearly showing his motion. So it's like the camera was staying still and it took pictures at a regular interval as the skier went over the jump. Okay, so let's describe what we see going on here in this series of images. What do you see?
He hits the ramp. As he leaves the ramp, he turns. He turns, and then right before he lands, he extends back out.
Okay, so there's actually a lot going on here. We see a rotation of the skier as the skier was flying through the air, right? What else do we see?
Projectile motion.
It is projectile motion. We'll talk more about projectile motion in a later chapter. But just on its basic level, let's try to just go basic here. So we see a rotation as the skier is flying through the air. What else is going on?
Crouching. He's like has his legs up to
What?
like cradle.
Well, when he
Cradles
jumps back
my
down.
All right, he does tuck up and then kind of extend back down, but just very basic. Don't overthink this.
Where's Karma?
The skier goes up and then back down. Okay? And also, so we have up and down, we have rotation, and also one more thing.
Landing is straight leg.
No,
No, I don't know.
because up and down, rotation,
Uh-huh.
acceleration, deacceleration.
Okay, so we have the skier went up and then down. We have that the skier rotated around.
And then we have him going forward.
The skier also was going this way. So we have three different motions of the skier going on in this one thing, okay? Through this series of pictures all kind of stacked up on one picture, okay? Now, there's other things that we can talk about here too. So if I'm able to put a grid down on this, I can't, but let me try to draw a series of vertical lines through the skier's head, okay? I'm trying to make these as vertical as I can, and it's kind of wonky because I think the skier is kind of going away from us as it goes. But maybe what do you notice about the motion of the skier as it travels from left to right?
Like spacing?
Spacing, sure. What do you notice?
It's getting smaller, so I think it's, heading away from us. Plus, we can see
Yeah, so he's kind of heading away from us, so this isn't the best example of it, but possibly
There's one each frame.
his movement is actually constant.
Yeah.
Okay? His movement in this direction is actually a constant speed. Okay? We can't really tell because I think the skier is actually moving away from us the whole time. Okay? Now, what if I drew grid lines this way? So here, and then here, and then here. I'll draw through both of those heads right there. And then here, and then here, and then here, and then here. What do you notice about those?
Goes like
Okay, we're going up and then we're going down, but what do you notice about maybe the spacing there?
It gets varied by how often the picture is taken.
All right, what did you say?
I wasn't paying attention. Oh, I'm lost.
What about the spacing here on these orange ones?
It varies because once you have enough thrust, gravity then starts to take over and pull you back.
Okay, yeah, gravity in the up and down direction here is playing a role. So we have gravity pulling us back down to Earth. And so even though we launch ourselves up with a great amount of speed, right, eventually gravity is taking over and it's trying to pull us down. So in the up direction, we're kind of slowing down, and then eventually we're stopping, going up, and turning around and coming back down, right? So we're going up, slowing down, eventually coming to a stop, and now we're starting to come back down. And what do you notice as we start to come back down about these lines?
Oh, they're getting more space. but
They're getting more spaced out, which means we're doing what as far as speed?
Well, because first
Speeding up.
they were really close together and now they're starting to expand out.
And so in terms of speed, what's happening?
The gravity.
Approaching terminal velocity.
He's
we're-
slowing down, or is he getting faster?
We're getting faster
Accelerating.
this way.
Because,
Right.
because before you're fighting gravity,
Uh-huh.
now gravity is accelerating because it's pulling down.
So what are we doing as we go up? Speeding up or slowing down?
Slowing down.
Slowing down. And what are we doing as we go down?
Speeding up.
Speeding up. What are we doing as we go this way? Speeding up or slowing down?
Speeding up.
Or neither?
Well, it depends on the angle.
If these lines are all equally spaced apart,
Well, that middle one, those two middle ones are,
Yeah.
yeah, it's tricky because this is kind of a bad picture, but
but in reality, it's probably going about the same.
we're going about the same. So we're not really speeding up or slowing down at all. So
So you're going the same speed going
horizontally.
horizontally, but
That's right.
vertically, you're actually accelerating when you're going down.
So let me ask you this. You guys know what independent and dependent means, right?
Yes.
Okay. Are these two motions here independent or dependent on each other?
They're
Independent.
They're actually independent.
Independent.
And
I thought you
then
said
what about this rotation here?
That independent.
Also independent. So we have three different motions going on here. Up and down motion, rotation, and horizontal motion. And all three of those motions in this one picture are totally independent of each other. Okay? That's the sort of thing that we can analyze with physics, with this class. Okay? And we gained all of that information by just looking at a picture. Okay? Not even looking at a video, a picture. It's pretty cool. All right? And that's what we're going to be doing in the first few chapters of this class. We're going to look at motion in one dimension, so just like horizontal motion or just vertical motion. And then as we gain skills, we'll start to look at two-dimensional motion, projectile motion. Okay? But before we can do anything, we have to start learning vocabulary. We have to start learning how to represent motion with vectors and learn about how to measure things and how to calculate things and how to properly write stuff. Okay? So that's the plan. Now, trigonometry is a major part of this class. So if you don't remember trigonometry from geometry, if you're in pre-calculus right now, you're going to get a big review of that. Here you go. We're going to review this sum here. So in trigonometry, you need to remember that we're dealing with right triangles. In this class, we're always going to deal with right triangles. So we have a right triangle right there. Okay, I know that because of the little box that I put there. So it's always going to be right triangle math here. Every day, for the most part, it's going to be a right triangle in this class when we're dealing with two-dimensional motion. Okay, so when we have a right triangle here, the hypotenuse is always directly across from the right angle. Okay? Now, we're going to need a reference angle. In this picture, they gave us our angle theta. That's theta. The Greek letter theta is our reference angle there. It doesn't matter which angle in the triangle is the reference angle. A lot of times it'll be down here and be that angle. That's okay. Okay. Up here in this triangle, this angle this time is our reference angle theta. All right. Now, the side that is touching the reference angle is known as the adjacent, and the side that's across from theta, a reference angle, is known as the opposite. Okay? Again, remember that the side that's directly opposite the right angle is always the hypotenuse.
Oh, yeah, no.
Okay? So we have a hypotenuse, we have an adjacent side, and we have an opposite side. Good? Okay. Now, I can call this A, and this O, and this H. The first initial of each of those words, just for simplicity, right? Okay. Now, what we have is a record-keeping tool of what ancient people from thousands of years ago figured out. They figured out that no matter how long I made these sides, as long as I kept my angle the same, so for example, if I do this very badly, right, if I extend this leg right here, I keep this angle right here the same. If I extend this leg and extend this hypotenuse down and connect that over there on the end where I ran out of room,
It makes another right triangle.
we have just a bigger right triangle. They're similar triangles. The angles are all the same. The ratio of these sides, like the ratio of this side to this side, compared to the ratio of this side to this side, is the same. Okay?
As long as
Ancient
you
people
get-
from thousands of years ago figured that out. The ratio of the sides will be the same. It doesn't matter how big or how small these similar triangles get, the ratio is always the same. Okay? So let me erase this. What they did was they started sort of a catalog of sides, side ratios, compared to the reference angle that they were talking about. So, oops, let me erase this too. I don't want to
Covered this
confuse
last
people.
year. This is like a review from Algebra 2,
It's a review from
or geometry.
geometry. Yeah. So what they did was they said, okay, let's talk about the ratio of the adjacent side to this reference angle and the hypotenuse. The adjacent side to the hypotenuse. We can make that ratio. And let's talk about the ratio of the opposite side to the hypotenuse. That's a different ratio. Opposite side to the hypotenuse. And let's also talk about the ratio of the opposite side to the adjacent side. That's a totally different ratio as well. Okay? So that's 3 different ratios. Now we could flip those. We could do this one over this.
H over.
We could do this over this, and we could do this over this. Those are basically the same ratios. They're just reciprocals of each other. Okay? So technically there would be 6 ratios, but really they're the same. They're just reciprocals of each other. Okay? So we'll just deal in these 3 right here. Make sense? Okay. Well, how are we going to refer to those is the question. Well, they're all ratios using this same reference angle right here. So why don't we call this one right here sine of that reference angle, theta. We'll call this one cosine of this reference angle, theta. And we'll call this one tangent of this reference angle, theta. Now I'm kind of simplifying what is really going on here, but that's the idea, okay? That's the concept of what's happening. The cosine theta is really just the ratio of the side adjacent to the hypotenuse. The sine theta is really just the ratio of the opposite side to the hypotenuse. And the tangent theta is really just the ratio of the side opposite to the side adjacent of the reference angle. Okay? And if you can remember those things, then you can handle all of the trig that we're going to do in this class. Okay? And we're going to do a lot of trig in this class because we deal in right triangles all the time in here. Okay? All the time. You have to know this. Now, if you can't quite remember these off the top of your head, then there is a little helpful mnemonic that we use, and that is SOHCAHTOA. SOHCAHTOA is simply the abbreviation of the first letter of each of these things. So is sine, is opposite over hypotenuse. Ka is simply cosine, is the adjacent over the hypotenuse. And toa is just tangent, is the opposite over the adjacent. To help you remember which one goes with what. SOHCAHTOA is easy to remember, it's kind of fun to say, and that helps you remember.
Sine makes it worse.
All right, so as the year goes on, you will see these types of problems where it says stop to think. So these are kind of conceptual problems maybe They might be problems that are similar to what we've just talked about. A lot of the times, it's going to be something that you can do in your head, or you might have to jot something down. It might be something that you need to work on with a formula that we just learned about, okay? But most of the time, it's something conceptual. So, on this one, it says, what is the length of the hypotenuse of this triangle?
So 6 squared times 8 squared is 36 plus 64. So 100, so then divided square, it'd be 10
Let's
centimeters.
just see, yeah.
Okay, so yeah, it's 10.
Yeah.
What?
Okay, so how did you do it? What did you use?
Pythagorean theorem.
Yeah.
Use the Pythagorean theorem. What is the
Oh,
Pythagorean
A
theorem?
squared- A squared C squared equals C squared.
Now, the only reason you can use the Pythagorean theorem is because somehow you knew it was a right triangle. It has to be a right triangle before you can use it. How did you know it was a right triangle?
Hypotenuse.
They said hypotenuse. Because it said hypotenuse, then you knew that it was a right triangle. Only right triangles have a hypotenuse. If it's not a right triangle, then you can't say hypotenuse, okay? So, that means we can use a squared plus b squared equals c squared. Now, c is the hypotenuse. So that means the other two sides, 8 squared plus 6 squared equals c squared. 8 squared is 64. 6 squared is 36. That's 100.
Square root of 100 is 10.
Square root of 100 is 10. These were centimeters, so we're talking about 10 centimeters. Okay, now, there is another way to do this. What?
Well, if there's like the box right there and all that, but it doesn't say hypotenuse in that word.
So if they gave you that, and they didn't say hypotenuse, well, you already know it's a right triangle anyway, so you can still do it, okay? If they didn't tell you hypotenuse and there was no box, you could not assume that this was a right triangle, okay? And then you would not be able to do this problem, actually.
Okay.
All right. There is another way to do this problem. You know it's a right triangle, and you see these side lengths here, 8 and 6. Knowing that it's a right triangle, these numbers are what's known as a Pythagorean triple. 3, 4, 5,
Oh, yeah.
right triangle.
And that's just.
These numbers have been multiplied by 2. The missing side is 5 in that basic Pythagorean triple. These have been doubled. 5 will be doubled. 10 is the answer. Okay? That's a useful thing to know if you haven't taken the ACT yet. Almost always there's a Pythagorean triple problem. You can answer it quickly. Save yourself some time. Okay? Pythagorean triples are like 3, 4, 5. If you double that, triple that, so 6, 8, 10, 9, 12, 15. Okay?
Oh, okay.
That ratio of sides there is a right triangle. So double it, triple it, multiply by 5, multiply by 10, stuff like that. Those numbers will always form a right triangle. Okay? 9, 12, 13 is another one.
And then there's
Or,
12.
sorry, 5, 12, 13 is
So
another
that's a
one.
good idea to try to get those and
5, 12,
memorize
13.
those.
Yeah. If you know some of those off the top of your head,
It'll help.
and
save
then
time.
you can double them, triple them, stuff like that, then it saves time if you are taking a test and you see one pop up.
5, 12?
5, 12, 13, man. Okay, so motion is something we're studying all the time, okay? As I said on day 1, there's 2 sides to this class. It's the study of things that are in motion, dynamics, and the study of things that are sitting still, statics. Okay, both of those things. So motion, we study all the time. You ought to have a pretty well-developed intuition of motion just by being alive, okay? But the most important aspects of motion are actually very subtle. So in this first chapter, we're spending time visualizing moving objects as well as developing the concepts needed to describe a moving object. So I've been kind of hinting at that all along so far, all right? So, types of motion. There are 4 basic types of motion. Straight line motion, you're driving down the road, you're walking down the hallway. Straight line motion is like that, roll a ball on the floor, okay? Circular motion, the guys here on the motorcycle going around the curve, you're driving your car around a corner, okay? All kinds of circular types of motion that we could be talking about. Twirling a ball around on a string, same ideas.
Are we gonna learn about, let's say with like with the guys on the bikes. Like, I know the rough idea of why, but we're gonna learn more in depth why it's like when they tip that far over, they don't just fall over. Are we gonna learn about that?
To some extent, yeah, we'll learn about that. Okay. Projectile motion here, and we just talked about the skier. That was actually projectile motion. If you don't think about the part where he was doing the helicopter, where he was spinning around. Okay. Projectile motion has actually two components to it: up, down, and the horizontal part. And then the rotational motion here, like we're spinning atop, gyroscopes, stuff like that. Okay. So in this chapter, we're focusing just on the straight line motion, the motorhome driving down the road, okay, or whatever, walking down a path, driving your car, rolling a ball, okay, stuff like that in this chapter, because it's basic. We're just getting started.
So
Yeah.
his was, what would be considered, what would be, what, projectile motion and rotation motion?
The skier,
Yeah.
mostly it would be projectile motion. We probably wouldn't combine the projectile motion with the rotational motion. That's too advanced for what we're doing in this class. Okay?
And would it be inertia for the reason why they don't tip over?
No, mostly friction. Okay, so first thing we're going to learn how to do is make a motion diagram. So if we took a video of a car, so we have a video camera set up, and it's recording, and it's not moving, the car is driving through the scene. Here's what we would see frame by frame by frame, maybe, okay? The video is recording images at a fixed rate. So it takes a picture, takes a picture, takes a picture, takes a picture. If you look at like the reel, right? Maybe 30 frames per second, that's pretty standard. So if we analyze those frames individually, we might see this. So frame 1, frame 2, frame 3, frame 4. Okay? Now, if we stack all those images up so that it makes one picture, just like we saw with the skier, we would potentially see something looking like this. Okay? Now, because the video camera was recording at a constant rate, 30 frames per second, at a consistent interval, we see this car, which was driving at a constant speed, this car at equally spaced intervals. Okay? Does that make sense?
Yeah.
Okay. So, because we have this car at equally spaced intervals, we can say that the car was driving at a constant speed.
Got cruise control.
Probably did have its cruise control on. Okay? All right. So now what we want to be able to do is represent. So we have equally spaced intervals, boom, 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 right? What we want to do is represent this motion with a diagram where we don't have to sit here and draw the car 4 times. We just want to be able to simply represent it, okay? So, what we end up with is a motion diagram then. And the, like motion diagrams can be represented very, very simply just by showing the important features of the diagram. So we have 4 examples here, and what we want to do now is be able to think about what's going on in each one. So if we're equally spaced, so equal spacing between each one of these figures, constant speed, okay? But what about here? The person is here, the person is here, the person is here, the person is here. What's happening? We're getting more and more space between each one of those figures. That means we're speeding up. What about here? We have figure 1, figure 2, figure 3, figure 4. We're slowing down. We don't know how fast they're slowing down, but we know they're slowing down, okay? And the reason we don't know how fast they're slowing down is because we don't have a scale here. We just don't know, okay? Now, what about here?
Same speed.
So,
Roughly.
and we talked about this with the skier, right? So if I drew lines here, what is the spacing between those lines?
About equal.
About equal. look pretty equal. So that seems like a constant speed in the horizontal direction. But this ball is not moving in just one direction. It's actually also moving up and down. So we look at the spacing now. I'm trying to draw these vertical, but it's not working. How about up and down? What's happening?
It's changing, it's not.
Quick on the rise, slower on the.
It,
On the way up?
it's same speed, but then once it hits the peak, it
Yeah.
slows down a
Slows
little
down.
bit, and then it goes back to its
Okay, good.
original pace.
So we said the horizontal speed is constant, and the vertical speed slows down on the up, speeds up on the down. Okay, so all of this, the constant speed, the speeding up, the slowing down, these are operational definitions. What we're doing is we're analyzing a diagram and applying concepts, okay? This class is all about analyzing and applying concepts. We do solve problems also, but we solve problems in the spirit of these ideas, where we analyze what's going on and we apply a concept, and then if there's a problem to solve, okay, then we go ahead and do that math, okay? But it's all about concepts. Understand the concepts, use the concepts. All right, so now, which car is going faster, A or B?
B.
Assume there are equal intervals of time between the frames in both videos. If this sentence wasn't here, we could not answer this question, okay? That is critical. Which one's going faster?
B.
Car B, absolutely. Even though one is going in the other direction, doesn't matter, okay? How do we know?
There's less
Longer
cars.
gap, there's a bigger gap.
There's a bigger space between here than there is between here. There's equal intervals of time between the car's pictures, okay? And because this car went a greater distance than this car went in the same amount of time, this one covered more ground, which means it went faster. It got farther in the same amount of time than the red car did. Therefore, it is going faster. That's how you explain that.
Going faster backwards.
So write the explanation down.
Yes,
Okay.
write the explanation down. So that covers it. That's the whole section. Again, it's concepts. Notice we didn't really do any math in this section. It was all about concepts, explaining things, understanding what was going on, drawing motion diagrams, okay? So on the homework for this section, you're going to draw motion diagrams. These are motion diagrams here, okay? Where you are actually drawing like the car or the kid on the skateboard or the skier going over the jump or whatever it is, all right? If you were to represent something with dots, that's not quite what they're after. So they want to see the actual figure, whatever it might be, a car or, you know, whatever, a basketball, something, okay?
Yeah.
All right, so that's it.